All right. So, okay, so just as a reminder, right? So we were talking about how all of these nice diagnostics, all these nice indicators that we have for outliers in influential cases are based on the idea that we actually only have one rascal in our data set. So that basically is that we have only one data point that's not well behaved. But that is rarely the case. So in most cases, we have quite a few data points that are influential and maybe not quite consistent with the other data points. And then, so we are encountering several problems, and the most important ones are called masking and swamping. So wanted to remind you, so with these brief demonstrations, right? So here in this left graph, right, so we have this single outlying point that pulls the regression line towards it, right? So that's an influential outlier. So you can see how huge the difference is between the regression line. So that results when this outlier is included in the analysis versus, so this regression line here, if the outlier is not included in the analysis. However, if we have more than one of these guys, right, if they're like similar data points that are still deviant from the rest of the data points in our sample, so then actually excluding only this one outlier does not change the regression function that much, right? Because the other guys here still basically maintain this pull, right? So that means, so all these detection methods for influential cases basically operate by only excluding this one case from the data set and then see how much the regression statistics change. And you can see here that if there are like many outliers so that are similar, right, in a similar range, then so excluding only one of them doesn't have that much of an effect. So we might actually not identify this outlier or this influential case as an actually influential case. So that is called masking, right? So the other outliers just mask the outlier status of this one point. And the same is true, of course, for all other points, right? So so the other guys here always prevent each individual point from being identified as an outlier. And so a related phenomenon is called swamping. And so swamping means that if we have masking, so right, if we have like multiple outliers that pulls a regression line towards them, then so the effect that these outliers have on the regression line, on the regression function, so might make a data point that's actually not an outlier appear like an outlier, right? So because they're pulling the regression line in a certain direction, and that might make a point that was perfectly well behaved. So if you would if you discount so this data point here, so then this one here, right, in relation to all others, is not an influential point. So it's very much consistent with the relationship so that is described by this line here. However, so if the line is pulled towards this group of outliers, this point here suddenly appears to be an outlier, despite the fact that's not. if you basically focus only on these well-behaved points, right? So and that is called swamping, right? So it makes a data point appear an outlier that's actually not an outlier. So, and these are problematic, right? Because what we want to accomplish is we want to not necessarily exclude, but we want these unusual data points, we want to understand the influence that they have on our regression model. And we want to get an idea of what the regression model would look like without these data points, right? And we want to understand what they represent. So, but it's hard. Basically, what we want to do is we want to accomplish, so we want to understand that these are outliers and those are not, right? So, and that is not always possible without any additional information. All right, so what can we do, right? That was the big question. And so there are two fundamental approaches for this problem. The first one is called the direct approach, and the second one is called the indirect approach. And the direct approach basically tries to to use different sequential algorithms to isolate outliers. So they basically try to identify the data points that are outliers, right? And they do it in a sequential way. So the indirect approach uses robust regression. The robust regression is basically just an alternative to the ordinary least squares regression, and it operates by either downweighing, right? So giving the outlying observations or unusual observations a lower weight in determining the regression function, so in determining our regression coefficients, or completely ignoring them. So, and these are the two approaches, right? So the first approach is called the direct approach because it's really focused on identifying the data points that are considered unusual, the outliers. The second approach is more indirect because it tries to come up, basically it is an estimation procedure, right? It wants to estimate, so the aim is to estimate a regression model, an equation, and it tries to minimize the influence of unusual observations when doing so. Okay, so and for the direct approach, we have two different varieties of these sequential mechanisms. So the first one is called the backward search, where we have a sequential deletion. So where we start with a complete data set and then basically one by one, we're deleting or removing, right, putting data points that are considered unusual or outliers in a different basically removing them from the data set, right, or isolating them. And then there's the reverse approach that is called forward search, where we start with a data set or with a subset of our original sample of our original data set that we assume is clean. And then we are sequentially adding cases based on certain criteria. So right, and for both the backward search and the forward search, there have different criteria for removing or adding cases have been suggested, and so for very popular or very commonly used for backward search algorithms are things like the largest absolute value of a transformed residual. So it's based on residuals, right? So the general idea is that we are moving cases based on their residual values, and so that those who have large residuals are the most likely to be removed. And of course, these are transformed residuals, because otherwise we would do the same thing that we do when we are basically trying to identify our outliers with the common methods, right? So we basically, those approaches take into account that the residuals might be influenced by other data points. All right, so but we could talk about basically you could design a whole lecture just on these direct and indirect approaches, so that's why we can't go into much detail. All right, so as I said, the forward search starts with an initial clean basis, so it's a subset of the original data set, and then so it basically adds sequentially data points to the subset until some threshold is reached, and then it just declares all remaining data points as outliers. And so usually the forward search mechanisms are better, so algorithms are better than the backward search algorithms. So in a very popular approach, also very actually a very efficient and so also superior to many other methods approach has been suggested by Atkinson and Rayani. And it starts, so as all forward search algorithms, with a small, robustly chosen subset of data. And then it says size P, so where P is the number of predictors. And so this that subset, so that subset of the data actually is not true. It's not the P is not the number of predictors. That is nonsense. Please scratch that. So and that subset of the data is clear of outliers, and so and then this, as I said, so to this initial clean data sets, we incrementally increase the size by adding more cases. So And in this algorithm, so they measure the agreement of each new observation. So the one that they hope it, so that they're basically considered to add to the clean subset. So, but it's a studentized residual, right? So, and so that means if the studentized, so they always add or consider adding a case that has a minimum studentized residual of all the cases that are not included yet in the data set, right, in the subset. And so, and then they also monitor other properties such as so the overall parameter estimates, how much they're changing, right, by adding this particular case, and whether the inferences change as the subset size increases. And so this method has in general good robustness to both masking and swamping, and it's implemented in the R package forward. So that is something that you can use. There are actually, I think, quite a few R packages that are implementing. So for robust regressions, there are many, and I think also for so forward search are a few that implement different algorithms. Okay, yeah, so the idea is, so right, we start with a clean subset, and then from the remaining data points that are not included in this clean subset, we're choosing the one that has a minimum studentized residual, and then after we have added that to the subset, we are checking different criteria, right? So how that changes the parameter estimates, how that changes the inferences that are made on this model that is estimated from the subset. And so based on certain criteria, so it is then determined whether so this additional data point can be included or not, right? And at some point, so if the change in the, for example, the parameters of the model is too large, exceeds a certain threshold, then so they stop, and so the algorithm stops including more data points, and so all remaining ones are declared outliers. So the second approach is called robust regression. And so I mentioned that earlier, right? So sometimes people differentiate robust regression from resistant regression. So they say, okay, so robust regression is just downweighing unusual observations, whereas resistant regression is actually ignoring those unusual observations. That means just not including them in the estimation of the regression model. So in almost all of these methods, so take into account the magnitude of the residuals, right? So that is almost always true. And so then they have different methods how they accommodate for the fact that the residuals might be influenced by other cases. And so, as I said, I don't want to go into much detail. Maybe that's something that we can get back to at the end of the semester. I just wanted to, basically, I have included in the slides, and so if you ever want to refer back to it, so you can do that, just to provide you with some basic information. There are quite a few robust estimators. Maybe we can include one example in our lab portion. Next week, I'll see. So the most common robust regression estimators are the last median of squares, so the last trimmed sum of squares, and so the so-called M and MM estimators. So and they are all the robust regression techniques basically are modifying so the way that the regression model is estimated. So normally in ordinary least squares regression, you're trying to minimize the sum of the squared residuals, right? And so, for example, a least median of squares, instead of this sum of squared residuals, it tries to minimize the median of the squared residuals, right? So for regression. So basically, you're estimating the regression model by just estimating by minimizing one individual residual, right? One individual value, right? So which is in this case supposed to be the most representative value if there's a median. Okay. So and the least trimmed sum of squares, so it's slightly different. So it tries to so also to minimize so the sum of squares, but sorry, sum of squared residuals, but it operates on a subset of observations, right? It does not include all data points. And the M and MM estimators are downweighing cases that are so based on their residuals. So that's the larger the residuals, so the less of an influence so this respective case has. And so they're basically, instead of just minimizing the sum of the squared residuals, they're minimizing a function of the sum of the squared residuals. And this function, so there are different alternatives for this function, and it's usually a symmetric one that has a unique minimum at 0. So in a way that, right, so if you basically, the larger the deviation, so the larger the residual, so the smaller the weight of this particular case. So, right, it's all modifications in the way that the regression model is estimated, right? So instead of the sum of squares, so the different, basically, so we are replacing that by something else or by a modified variant of that. Okay. And still another approach is, so in addition to all those that I mentioned, is just to replace a normal distribution of the residuals with some heavy tail distribution, for example, a T distribution, right? Or also a mixture of normal distributions with different variances to account for the fact that the right, so the residuals might not follow a normal distribution. So these are also options, right? That fall, so that can be subsumed under this big umbrella term, robust regression. So there are many, many, many vastly different approaches. Okay, so as I said, maybe we can cover one of them in the lab part. Alrighty, so then I would basically skip probably all these things here. So we have talked about the bootstrapping already, right? So, and just as a reminder, I mentioned that yesterday, bootstrapping is an alternative that we want to consider, and the assumptions of our for inferences of our regression model have been violated. Yeah, so like the normality of the residual distributions of our error distributions, or if you have heteroscedasticity. Bootstrapping does not per se help with so if you have like so identifying influential cases or dealing with the distortions that are introduced by if we have a lot of influential cases, right? So that is something that bootstrapping cannot do. Whereas the method that we have talked about before, right? So robust regression. So they're very impressive, and their results in the sense that they can deal with situations where 50% of our data points are actually contamination. So contamination means that they're outliers, right? So, and they can basically estimate a regression model, especially so as a last median of squares, not especially, but the last, this is only true for the last least median of squares and least trimmed sum of squares. So those two estimators, robust estimators, can deal with as many as 50% outliers in our data set, which is quite impressive, right? And they can basically separate them and come up with a estimation of a model that does not include those data points. And so for bootstrapping, there is no way that bootstrapping can accomplish something like that. So it will basically fall short the same way as ordinary least squares regression if we have a situation like that, right? If our data, so if 30% of our data are outliers, so that are from a different population, for example, or that are where there are errors in our measurement or data entry. So it's something that bootstrapping cannot deal with, right? So it does not offer a solution for that. Okay, and then of course the data has to come from a random sample, but this is true for all methods. So if you don't have random samples, then nothing we can do, yeah? So no robust regression will help us with that. So the same as with independent errors. So it always, right, for all statistical tests, I repeat that frequently, so I want you to remember that. So there is there are two assumptions that we can never give up, and there is no way to correct for them, or we have to have a random sample, and we have to have independent errors. So there's no way to get away without those two. Okay. So, and IFI, right? I mean, I think I mentioned that yesterday too. So bootstrapping alone cannot help it. If you have a heavily contaminated data set, but you can combine bootstrapping with methods of robust regression. So that is possible, right? And then you can deal with the situation. All right. So, and then another big question, and I think we have talked about that before as well. So once we have identified our outliers, so what should we do with them, right? And we mentioned that earlier, so that it's not appropriate to, without further checking, to simply exclude those data points. There might be valid data points, right? So, and if we identify, for example, using, right, so Cook's distance or other diagnostics, if you identify a data points that are influential, so then it just means we have to check those data points. We have to make sure that they don't reflect any obvious errors. And if they don't, yeah, so then we want to understand how they influence a regression model and why. It does not mean that we simply exclude them and say they're just faulty observations. You know? So we want to understand them. They might be valid data, so they're right. If there's no reason to believe that they're not valid data points. Okay. So, and therefore it is very important. So in deciding what to do with outliers is to find out, is that a contaminated observation? Is that an erroneous observation? So did something go wrong? Or is it just a rare case? So a rare case is a valid observation. It's something, nothing was wrong with measurement or whatever, right? So it's just a rare case. All right. So if we have contaminated observations, so then this is a high influential observation that is inconsistent with replications of the experimental design. So that means if we would replicate our study, right, so then we wouldn't be able, so we probably wouldn't get this observation again. So then our regression model is again in the long run, right? So it would change. So we wouldn't, that is something that wouldn't happen again, right? Because it's like some unique error, some unique mishap. And then, I mean, we talked about that earlier semester, right? What all the things that can go wrong, right? So, and that reflect those contaminated observations. And those are cases where, so a deletion of these cases, if you cannot correct the errors, then it is appropriate to delete those data points, right? So just remove them from your data set. But so the most important aspect is that you should be able to identify those contaminated observations a priori, right? So you're not only identifying them based on the fact that they are influential cases and that some statistics are high for them, right? So you have to be able, so based on your knowledge of the design and what you expect, right? So what's reasonable for your data, you have to be able to define those. That is not a possible value. All right. So, and the other alternative is that the outlier is an extremely rare case. And if it's an extremely rare case, so then we, as a default, we usually do not want to exclude them, but we want to understand what they mean, right? So we have to take them into account. That still, it means, of course, it is one option to calculate our model without those cases, right? But we also want to calculate it with those cases, and then we want to relate the two outcomes with each other, and we want to come up with an hypothesis about why we see those changes and what they signify. All right, yeah, so extremely rare cases might be a college freshman that is 12 years old and has about 800 SAT in math. So that is possible, right? So it's still a college freshman. It's just a very unusual case. It doesn't mean that there's some error, so that is not a contaminated observation, just something that is very rare. And so rare cases, of course, so they so can result from different things. It can result from the fact that the actual distribution of variables represents a mixture distribution. Yeah? So, and that you have like different subpopulations, or that you have that in your population you have subgroups that have a different, so whereas you have a different relationship between your predictors and your outcome variables. So, and it's also possible that your dependent variable may be one that naturally gives rise to extreme cases. Yeah, so that shows a number of absence, so sick days for employees in a firm in a given month, right? So that is something that naturally gives rise to extreme cases. So it's also possible that your regression model is simply incorrect. Yeah, so for example, your actual relationship might not be linear, might be non-linear, So these are all reasons why you get observations that do not fit your model very well, right? So, and you have to, your task is to find out what's going on. So why is that? And say if I didn't do anything wrong, if I didn't make mistakes in my experiment, so why do those cases don't fit so as a regression very well, and how can I improve my model? So what additional variables can I take into account? What interactions? So how can I model the relationship better? All right. Yeah, and so just to sum up, so if our sample size again. So, so the effect of an outlier is larger, so the smaller our sample size, right? If we have a huge sample, then probably a few outliers don't have a big effect on the model as such. Yeah, so and then outlier deletion is basically only an option if we can be sure that our cases are actually really contaminated observations, so that there was some sort of error in the process. So the second option that what we can do when we detect those outliers or influential cases is to respecify our model. So we could do a data transformation, right? So we did that yesterday, right? We could simply try to do a square root transformation to if you have a highly skewed, or like a log transformation if you have a highly skewed distribution, right? There's a lot of extreme cases. Mostly it's like a positive skew, it could also be a negative one. Or I fit a polynomial model, right, where I have, for example, a quadratic term, a cubic term, and then, at some point, of course, it gets meaningless. So we always want to be sparse in our model specification. So we want to have the simplest model possible, because, of course, if I use a polynomial regression model, and you remember that from algebra, so then I can fit, or calculus. So then we can fit basically, if you just add enough terms, right? So then we can basically perfectly fit any function. So, but that is meaningless, right? So it's just descriptive. It's not certain with the model we always want to explain. We want our model to be parsimonious, right? Parsimonious. So we want to be the simplest possible model. Okay. And so then the third option, of course, is to use robust techniques. So and that can help us with, especially with contaminated observations. It can also help us understand what's going on if we have rare cases that do not reflect contaminated observations. Okay, right. And so the second option is so basically that's a way to go if you have those rare cases. So usually you wanna respecify your model, and so the robust techniques are more, so in case of the rare cases, the robust techniques are more to help you, an additional means to help you better understand what's going on. All right. So another aspect that is very important is that we are doing the entire regression thing because what we actually want is we want to make predictions based on our regression equation, right? So, and once we have shown that our model is an appropriate fit for our data, we want to use our regression model for predicting the outcome variable. right? So for new data, right, or future observations. So yeah, so if we go back to our example with the album sales, and right, so if our regression model was the 88.97 plus 3.87 times x, so the numbers of the sales are, so basically the predicted sales follow this equation. Then if you want to find out, so for like a certain amount of okay, it's actually not the an investment here, it's a number of times a song was played on the radio. So if you, for example, wanted to find out, okay, so if I play the song 3 times on the radio, so how does that change so the mean number of album sales? Let me just put that in basically plug it into our regression model. And so we come up with a solution here. So that gives us the estimate of so roughly 100,000 albums more that are sold if that song is played 3 times on the radio. All right, and again, so keep in mind that is the mean value, right? So of course the actual values will differ, so will fluctuate around our prediction. But now, so suppose that we want to estimate an actual value of y. Yeah, so when x equals a certain value. Yeah, so we want to estimate the actual value, so the actual number of album sales when we play the song 3 times on the radio, rather than just the conditional mean. Yeah, so we do not only want to predict the the mean of all albums that are played 3 times on the radio. We want to know for like this particular one. So what can we expect? And so the problem is that the only estimate that's available for an actual value of the sales is our expected value, right? So for this conditional distribution. But it is a random variable. Whereas, so our expected value for the conditional distribution is a single parameter, that's a constant. And therefore, we cannot expect to estimate our actual sales numbers as precisely as we can estimate our conditional mean, right? So that means our, so our y hat prediction is always more precise naturally than so the prediction of our actual outcome variable, right? So of the actual value of the actual sales number. And even though our y hat is a good estimate of the conditional mean, it might be a very crude estimate of an actual value of the outcome, right? So even though, right? So if even though 100,000 might be actually a fantastic estimate of the mean sales numbers for all albums that are played 3 times on the radio, it might be that, right? And let's say it would be like 1,000 albums, right? So we have 1,000 albums, and each of these albums is played 3 times on the radio. On average, so if we basically, that was our entire population, right? So I mean, not 1,000 albums, but they're so there are these 1,000 albums that are played 3 times. So and if we would calculate the mean, right, for all the 1,000 albums that are played 3 times on the radio, then it might be a value that is actually pretty close to this estimated 100,000. However, for the individual albums, might be that one sells only 10,000 times. Another one might sell 1 million times. Another one might sell 10 million times, who knows, right? So that means that this 100,000 might actually, for each individual album, it might be a really poor approximation, even though the mean, right, of the 100,000 might be a fantastic estimation. So it depends on how much, right, how wide our conditional distribution is, how good our model is. All right. So, and that is, right, of course, something that we have to keep in mind. So And we know, right, that the uncertainty in our estimate of our outcome variable is greater than our uncertainty of the mean, right, of these conditional distributions. So, and therefore the confidence interval for a conditional mean underestimates the uncertainty in our use of y hat as an estimate of the value of right, of the actual album sales, right? So if that, let's go back to our example, if that album, for example, is played 3 times in that week, right? So we have here, and you see that here in this graph on the right. So if that's our regression line, then here we have our confidence band, right? So that's our confidence interval around the regression line. And then again, that is the confidence band for the mean of the conditional distributions, right? So the mean of the albums that are played 3 times or 4 times or 5 times or 6 times. But then, so this here, so this confidence interval that is called the prediction interval is actually a confidence interval for the particular outcome value, right? The confidence interval. So and of course we have to use y hat. We have nothing better, right? So we have to use our regression line as the estimate. But of course, the confidence interval for the actual values is much wider, right? Necessarily. So, and that is called the prediction interval, right? And it takes into account the variability in the conditional distribution, so how much the so the actual sales numbers, right, deviate from so the predicted sales numbers. As I said, could be something like, right, it could be range between 10,000 and 10 million if we are unlucky. And it takes also into account the uncertainty of our estimate of the conditional mean. So it basically takes into account that there's a certain, of course, an uncertainty in as to how much our regression line actually, the true regression line, right, in our population. So the true conditional means, how much they vary. So how much our sample estimate might deviate from this true regression line. All right. So, and so I just wanted to remind you, right, so that it is very difficult to make valid prediction outside the range or X range in the sample, right? So just keep that in mind. So so as soon as we basically try to make predictions that is outside of our X range, so our estimation or prediction error gets so large that these predictions are meaningless. So basically our model is only valid, so our predictions are only valid for the X range that we have in our sample. All right, so but let's go back to the prediction interval, right? And the predictions, so the uncertainty that is associated with the prediction of individual values based on our regression equation. So that means, so what you just talked about, right? So how much uncertainty we have in estimating this individual data points. So so the width of our prediction interval depends on several factors. So 2 factors to be precise. And the first one is the variance of our y hat as an estimate of, so the actual outcome or the the actual y value under the condition that x equals a certain value, right? So how good of an estimator are these 100,000 albums for one particular given album that was played 3 times? And then again, that might be, it might sell 10,000 times, it might sell 10 million times, right? And so how good is this 100,000 as a predictor for a particular outcome value? And so, and this variance is, so it equals the sum of the conditional variance, right? So how much the, variability we have for the outcome variables under, so this assumption that, so given that our predictor has a certain value, and the variance of y hat as an estimator of the mean of this distribution, right? So it depends on the variance of our conditional distribution and the variance of y hat as an estimator of the expected value of this distribution. Okay, so yeah, again, it's basically this uncertainty and this uncertainty here, right? And typically, so our conditional variance, so how much the, sorry, let me go back to that. So how much our, so let's assume we knew what the true regression line is, right? So let's assume in this case, which is not true, but let's assume in this case, so that would be our true regression line, right? So it's a true population regression line. So then our conditional, so the variability of our conditional distribution would be the deviation of the outcome values from this true regression line, right? So how much our, for each of album, so that is right, played 3 times, how much do the actual numbers deviate from this true mean that might be 100,000, right? And that is, so this conditional variance is typically larger than our uncertainty of how good our 100,000 estimate is, right? I mean, with the 100,000, we might also be not 100% right. It might be 110,000, it might be 90,000. But usually there's an error that we're making in this, in the regression line, right? So this predicting the mean of some conditional distribution is much smaller than the actual deviation of the outcome values from the true regression line. And so also the larger our sample, the smaller is our uncertainty that comes with the regression line itself. All right, so and the variance of, so that is the first part, right? And the variance of our regression line, so of our y hats as an estimator of the mean of these conditional distributions, right? The mean of the, as the expected value of these conditional distributions. So it depends on our, basically the variance of the conditional distribution itself and the distance of the predictor value x from the mean value of the sample. Yeah, so that means the accuracy of our prediction will be better if the x value is closer to the mean of x. Well, it means if the 3 times the song was played on the radio, if it's pretty close to, right? So if the mean is like 5 times perhaps, now 4 times, so then our the variance will be smaller, right? So the accuracy of the prediction will be better. If it's further away from the mean, if the mean is like 20, then the prediction will be poorer, right? The accuracy will be worse. It depends on the sample size. So it's larger, it's better for a larger sample. And it also depends on the sum of the squared distances of the predictor value from the average of the predictor values. So these are the different components that basically go into that uncertainty that is associated with the regression line. I know that was very dry, and so you probably have to read over that again so at home. It is important though. So, and I hope so that the figure here will help understanding it a little bit better. So the most important takeaway is, right, we have 2 components of uncertainty. One is basically our estimated regression line will probably deviate from the true regression line as a population. And then the other aspect is that the actual outcome values deviate, so how much they deviate from the true regression line, right? So these are our 2 components that determine how basically variable our predictions or how good or useful our predictions based on the regression equation are. All right. So the last thing that I wanted to talk about when it comes to simple regression is power analysis. And so it's mostly focused on R. So we can use R's PWR package to find the sample size that is required to have sufficient power for testing the significance of either correlation or R squared. So that's pretty straightforward. And so if we have correlation, right, so we can use R as an effect size measure, and we use F squared for as effect size measure for regression, right? And F squared is simply the coefficient of determination, so R squared over 1 minus R squared. So that's basically the variance in our portion of variance in our outcome variable is explained by the regression model divided by the portion that remains unexplained by the regression model. Right, then there are certain conventions, what constitutes a small, medium, or large effect size. And then, so if we do that in R, so and let's assume you wanted to determine what is a sample size that is required to detect with a power of 0.8 and an alpha of 0.05 and observed correlation of 0.3. That is statistically significant from 0. Right, so what would be required? So then you just call PWR test, and you give it all these specifications here as arguments, right? So that is what you want to see. It's your observed correlation, it's your significance level, power is supposed to be 0.8, and then, right, you want for a two-sided test, and then R spits out all the things that you need. But most importantly, the required sample size, which in this case would be 85, right? So, so pretty straightforward. And it's so similarly simple for regression analysis. So let's assume, so the only thing is you have to do a little bit mental arithmetics. So assume now that you can even do that in R. So that you want to determine the sample size that is required to detect again the power of 0.8 and an alpha of 0.05, whether in R squared with a medium effect size. So medium effect size is 0.15, so that corresponds to an R squared of 0.13, right? So just basically calculate that based on this formula here, right? So that's the only thing that you need to convert. That is statistically significant from 0. And here you use the function PWR-FR test. And then you have to give it so slightly different arguments. So you have the first one here is a U, and that is just the number of predictors in your regression model. So in this case, it's 1, right? And then you have so the argument F2, which is so your which is your effect size, the significance level, and the power, right? And then what R spits out is again, so it's just a reiteration of what you put in, right? So the number of predictors, then it gives you this value V, and so this is basically just what you have put in, right? So as the arguments, and this V here is a DF, so the degrees of freedom. So is your model, so basically your denominator. Not the numerator, it's the denominator degrees of freedom. So your residual degrees of freedom, so or error degrees of freedom that you, and then you have to convert that into the required sample size. And we know that so the sample size N is so the number. So it's our degrees of freedom, right? So for the residual degrees of freedom plus a number of predictors plus 1. So it's a degrees of basically the degrees of freedom plus our parameters in the model. And so if we apply that here, then we come up with a sample size of 55 that's required, right? So from what the residual degrees of freedoms are that this function returns. All right, so pretty easy. All right. Okay, then let's move on to multiple regression. All right, second. Okay, we go back to start here. All right, So multiple regression, so it's nothing but a natural extension of simple regression. Yeah. So we again we want to predict the value of an outcome variable, but this time not from one predictor but from several predictors. And so this is simply a hypothetical relationship, so a hypothetical model of the relationship between so this outcome variable and several predictor variables. Right. So the same way that we had a model of the relationship between a single predictor and the outcome variable. And so it's not actually a regression, not really an equation for a straight line. It's the equation for a hyperplane, but so we will talk about that in a second. So typically, so we don't have this notation with alpha and beta anymore. So we have the intercept that is usually denoted as beta 0. And then we have for each of our predictors here, right? So it's the first predictor, second predictor, plus, 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 and the nth predictor, right? And of course our error term. And then we just label the regression coefficient according to the number of the predictor, right? And then of course it doesn't matter which one comes first and which one comes last. So, and I will try to follow this notation here. I think it was not super consistent in my previous slides, so that whenever we have the Greek letters, we are talking about the population parameter, and whenever we have the Latin letters, we are talking about the estimates, right? So for estimates from our sample. Our beta 0 is our intercept. That's the expected mean value of y when all our predictors are 0. Yeah? So it's very similar to simple regression, but now all predictors have to be 0, right? Not only this one predictor. And it is a point at which our regression hyperplane crosses the y-axis. And this hyperplane, so hyperplane is a subspace. And so there's a subspace that whose dimensionality is one less than so the number of predictors in our basic, or the numbers of parameters our model. So it's basically the dimension is equal to the number of predictors. If we have 2 predictors in our regression equation, then our regression hyperplane is simply a 2-dimensional plane, right? It's what we normally refer to as a plane. So we will have a figure on the next slide that shows that hopefully a little bit better. So, right, that means in simple regression, we had a 2-dimensional space, right, model space, and then we had the 1-dimensional line, regression line in the space. So now, for example, if we have 2 predictors, we have a 3-dimensional model space, and we have a 2-dimensional plane for that describes our regression model within the 3-dimensional space. Okay, and then keep in mind, right, so that the intercept is only meaningful if so 0 is a meaningful value for each of the regressors, so for each of the predictors, right? So predictors, explanatory variables, regressors, so all the same. Independent variable, so they're different notations. And then the beta I, this is just our regression coefficient for our ith predictor variable, right? And it's a gradient or the slope of the regression in that particular direction. Yeah. And so if you basically interpret it in the same way as we interpreted so our slope in the simple regression model, more or less. So it means if you change your predictor by 1 unit, how many units does your outcome variable, so your y value change? And the condition is that all other predictors are kept constant. Yeah, so that is how we interpret our regression coefficients. So it's basically, you can interpret it very much like a simple regression coefficient, like a slope in simple regression, but the condition is that all other predictors are kept constant. Okay, so in here we have like a basically visual illustration of this regression hyperplane for two predictors. So now we have a three-dimensional space, right? So here, that is our basically outcome variable here, y axis. And then we have two x-axis, right? So one for the first predictor and the other one for the second predictor. And instead of a regression line, we now have a two-dimensional regression plane, right? So that's described by this equation here, right? So this is our regression plane. And you can see that it has a slope, right? So in the x1 direction, and it has a slope in the x2 direction, right? And so that means that, and this slope here, right, in the x2 direction, that is simply, so you can interpret that as like a, so this line here, right, that is simply the same slope as in a simple regression model if your other predictor variable was zero, right, were zero. And the same is true here, right? So the slope along the, so the the slope along your x1 dimension, so that is simply so the like the slope in linear regression, but again, so your predictor, so the other predictor variable, in this case x2, has to be zero, yeah, or constant. I mean, this is just zero is for this particular case here, where so you look at the edge of the of this plane, but of course you can put it everywhere, right? So you have the same slope no matter where you place the so your predictor value. So it could, the important thing is it's constant, right? So it doesn't necessarily have to be zero. All right, so right. I hope that makes sense, right? So you have basically, so you have this plane is basically you can that it has basically two slopes, right? So one along the x1 axis and the other one along the x2 axis, right? So these two dimensions. It's basically, if you think about, I mean, if you can, maybe if it helps you, and I usually do that in class, if you just take a sheet of paper, right, and then you basically put that into different angles and try to align it with your, right, so then to basically project that onto your imaginary axis, then maybe you get a better idea of what that means. It's always hard to depict it in a figure. Actually, it's often better to do it yourself. All right, and so this is for so our, again, like slightly augmented album sales model. So here again, right, our outcome variables. So these are the album sales in thousands, and so this is our regression plane here in our three-dimensional coordinate system. And here is the number. So we have the first predictor, that is the number of times a song is played on the radio from that album. And here we have the advertising budget, so how much money is spent on advertising. And then we have, right, so here, so the angle of the plane in the direction of, so your first predictor variable, that is the, right, that is the slope of your regression function in this direction. So assuming that advertisement is kept constant. And then you have the slope in this other direction, right? So the slope along this dimension. So that is just, right, that's the angle between, so this and this. And that is just basically the, so the influence of advertisement on album sales if you keep airplay constant, right? So just something that I wanted to say and I forgot. What did I want to say? No, never mind. And then the intercept, so that is the same as for our simple linear regression or bivariate regression, right? It is just, so the point where so this plane cuts through the y-axis. Okay. So and this is a cloud, right? That's a cloud of data points in this three-dimensional space. So they're floating around the three-dimensional space, and they clutter around the this plane here, right? So and they can deviate obviously in both in this direction and in this direction here. Okay. Nonsense. So now, of course, in addition to of course, these are deviations in our outcome variable, but so they have like an added dimension to it. So they spread over across these two dimensions. So that's what I meant to say. Okay. So the way we are estimating our regression model in multiple regression is very much the same as we estimated our simple regression model. So we simply so the criteria exactly the same. So the sum of the residuals has to be 0, and so the sum of squares has to be so the sum of the squared deviations has to be minimal. So that's how we estimate the model. So it's ordinarily squares regression the same way that we estimated the other model. So nothing new here. Okay, I mentioned that before, right? So what we wanna keep in mind, so except for so this like a slightly more difficult to visualize hyperplane idea is that in multiple regression, a slope describes the effect of a given predictor variable by controlling for the other predictor variables in the model. What does controlling mean? Controlling means holding them constant, right? So what is the change in the outcome variable as this particular predictor changes while holding all other predictors constant? Yeah, so whereas in our bivariate regression where we had only one predictor, so we were ignoring the effect of all other possible explanatory variables, right? So here we are controlling them in multiple regressions. So everything that's included in the model is controlled. Of course, everything that we do not include our model is also ignored, right? So we're just controlling the additional predictors that we're including. Whereas in so bivariate regression, of course, we were ignoring everything but the one predictor that we had in our model. So in if we take this example, right, for album sales, so if so let's assume our regression rate for again I call it, so for advertisement budget would be 0.08 and for airplay would be 3.37. So then it means as advertisers increases by 1 unit, so which in this case corresponds to £1,000, then album sales increase by 0.08 units. So 1 unit is 1,000 albums. So that means for every £1,000 that we spend on advertising, we sell 80 more albums. And this interpretation is only true if the airplay is held constant. And then same is true for airplay, right? So the number of times the song is played on the radio. So here's the regression rate is 3.37. So that means as the number of times as a song is played on the radio increases by 1 unit, so which is 1 time played, the album sales increase by 3.37 units. That means so every time a song is played on the radio, an extra 3,370 albums are sold. And again, this interpretation is only true if the effect of advertising is held constant. So something that is done quite frequently in multiple regression is to standardize the regression coefficients. And so the standardized regression coefficients for predictor variable just represents a change in the, again, right, in the mean of our conditional distribution of the outcome variable in standard deviations of the outcome variable rather than units. Yeah, so that means how many standard deviations does the outcome variable increase, decrease, whatever, change if the predictor changes 1 standard deviation? So controlling for all other variables in the model. And so then there are different ways to denote those standardized regression coefficients. I think I mentioned it earlier. It's super confusing because sometimes they're actually called simply betas, and where betas are more frequently so referring to the population regression coefficients, right? So, but that is sort of like a mix-up and can be super confusing. So, and I think the textbook called them, so marked them as a star, which makes more sense. So these are basically the beta star, that's a true standardized regression coefficient. So these are the standardized population regression coefficients, and the B stars would be the estimated standardized regression coefficients, right? Estimated from our sample. And the idea behind the standardization is that basically, right, so you want to express everything in standard deviations. And the idea is to make the influence or the contribution of the individual predictors comparable, right? So because, I mean, otherwise the regression weight, as we have seen in our example here, right? So because advertising was had a completely different units and so number of times the song was played on the radio. So this regression weight here appears to be much, well, not appears to be, but it's much smaller than the regression weight for this predictor. And then so people thought, well, wouldn't it be nice if you could directly compare how much influence a given predictor has on the outcome variable, irrespective of its unit, so of its scale. And that's how so these standardized regression coefficients came into play. So the idea behind that is that you can directly compare the contributions. So that means if all regression coefficients, so if you focus on the standardized regression coefficients, then a larger standardized regression coefficients also means like larger influence, larger impact on the outcome variable. Although you have to take that as a grain of salt, but yeah, so that's the underlying idea. All right, so if we have a simple linear regression model, then standardizing our regression coefficient obviously yields the correlation. So in this case, our regression coefficient or standardized regression coefficient would just be the correlation between our predictor and our outcome variable. However, for multiple regression, our standardized regression coefficients do not fall within the limits of -1 and +1. That means they can be larger or smaller, right? So then -1 and +1. Okay. Yeah. So, and so of course the test, because, right? So because one equals 0 when the other does as well. So whether I'm testing that my standardized regression coefficients are 0 is the same as testing that my unstandardized regression coefficients are 0. Yeah, so that does not change. So no matter whether they're standardized or not, so whether their scale changes or not, so when one is 0, then the other one is 0 too. So that's why it does not affect the significance test. All right. And then of course, so standardizing the regression coefficients, so will also, I mean, you basically, you can come up, so similar vein with a standardized version of your prediction equation. So if you simply, let me start over. So one way to think about the standardized regression coefficients is that, so those are your ordinary regression coefficients if you just standardize, if you just z-transform your all your predictors and your outcome variable, right? So if you basically make them all have a mean of 0 and a standard deviation of 1, then your regression coefficients, when doing like just a regular regression analysis, would be the betas, right? So they would be identical to the betas, because then you're doing what you're trying to accomplish, right? So that's how you basically, so that's what the standardized regression coefficients basically represent, right? So if all variables are on the same scale, what is the influence of each individual predictor? That it means, so if we standardize all our predictors and our outcome variables, so then that changes the regression equation a little bit. So we have now, so the predicted Z value of our outcome variable. So that is a sum, so a weighted sum of our Z transform predictors. And so where our regression weights as a standardized regression. So then we don't have an intercept anymore. So that is also, that is pulverized because there's so no mean difference anymore. Okay, so this is just a numeric example for interpreting the standardized regression coefficients. So for our example with the album sales, so as a function of advertising and airplay, so we would come up with so regression coefficient for advertising of, so a standardized coefficient of 0.523 and a standardized coefficient for airplay of 0.546. And now we see they're actually super similar, right? So they looked so different before, but now they are, so we see that they're actually, so, right? So the effect on the album sales, and that's what, yeah, if we were a record company, so that's what we would care about. So we want to know what is more effective, right? And so that the standardized regression coefficients help us making a decision, right? So say, okay, so that is equally important. But then again, so I mean, of course, as a record company, you have to take into account what are the cost associated with each measure. Yeah, just because that is now expressed in terms of standard deviation still doesn't mean that. So it's basically the cost benefit ratio is the same. Anyway, so the idea is that you so if you increase your advertisements by 1 standard deviation, whatever that may be, then the album sales increase by 0.523 of a standard deviation, right? And that's, of course, so that's 1 standard deviation advertisement, 1 standard deviation sales. And so here it means correspondingly, so when the number of times the song is played on the radio increases by 1 standard deviation, its sale increases by 0.546 standard deviations. And then you can transform that into real numbers, what we did before, right? So, which is probably not 100% the same, but anyway. So that means, yeah, so because the standard deviation of advertising is 485,655, right? And for album sales, 80,699. So then that means as advertising increases by 1 standard deviation, so by 485,655, then album sales increase by, so roughly half of the standard deviation, so 42,206. Whereas if the number of times, so the song is played on the radio, if that increases by 12, right? So 1 standard deviation is 12 for the number of times it's played, then album sales increase by also roughly half of this standard deviation of sales, 44,000. Yeah. All right. So whether that I'm not 100% sure whether I agree that this is actually helpful, because it still depends on what the range is for so for the predictors, but anyway, so you see it quite frequently and it might be helpful in certain situations. All right, so let's talk about the R squared. So we so now that we have multiple regression, we call our R squared multiple R squared. And before we're talking about multiple R squared, so first want to talk about multiple R. So the multiple R is our correlation between the observed values of the outcome variables, so between our Y values, and the values that are predicted by our model, so the Y hat. So it's a bivariate correlation between our Y values and the Y hat values. And you could also interpret it, of course, as a combined correlation, right, between all your predictor variables on the one hand and your outcome variable on the other hand, right? So it's a bivariate correlation between your Y values and the Y hat values, so what's predicted by your model. And then we have the multiple R squared. And that very much in the same way as was the case for our bivariate regressions or simple linear regression. It's just a proportional variance in our outcome variables that is accounted for by our model. So that can be explained by our model. It's also called the coefficient of multiple determination, right? So, and it's, right, that didn't change. So it's the same as true, what was true for our simple linear regression. So the R squared is just so the difference between the total sum of squares minus the residual sum of squares, so that's the regression or model sum of squares, so divided by the total sum of squares. So it's basically the ratio of the model sum of squares, that's the regression sum of squares, what is a variance that can be explained by our regression model, over the total variability in our outcome variable, right? And so this is just calculates as a total variability, just as a reminder, right? Sum of squares is just the sum of the deviations of all data points from their mean, right? So all outcome data points from the mean minus, so the deviation of the data points from the estimated values, right? So that's the residual sum of squares here. So it's a deviation from the regression line, and that divided by the total sum of squares again. Okay. All right, so properties of R squared are the same or very identical to those of R squared for the bivariate models. So it always falls between 0 and 1. So the larger it is, so the better the set of explanatory variables collectively predicts Y. So all together, right, all combined, means always our model. R squared is always about the model. The models are all predictors, right? So in simple linear regression was only 1. Now we can have as many as we want. And R squared always refers to the entire set of predictors, the entire model. So R squared is is 1 only when all residuals are 0. So that is if we have like a perfect relationship. So that means that all Y values exactly correspond to the estimated values. Yeah, so perfect predictions. And R squared is 0 when all our regression coefficients are 0. That means in this case, the Y hat is identical to Y squared. Yeah, because the explanatory variables do not add any predictive power. So they don't improve our prediction. And correlation is 0 between Y and each explanatory variable if R squared is 0. Okay, so then we have talked about that before as well. So R squared cannot decrease when we add another predictor to the model. So, and it is impossible to explain less variation in our outcome when we're adding another predictor to our regression model. And so that means R squared, so in basically that is true. And we know that R squared tends to overestimate the population value anyway, because so it cannot be smaller than 0, right? Cannot be smaller than 0. So we have this positive, so basically it's positive bias. And this bias is worse if we add more predictors to the model, because the predictors can only make the model better, even if the true effect is 0. So basically that's why the more predictors we have in our model, the more positive bias we have in our R squared. Right? And that's why our adjusted R squared decreases as the number of predictors increases, everything else being equal. Right? So the more predictors we have, if we have the same R squared for 2 models, one has 2 predictors, the other one has 5 predictors, then our adjusted R squared will be smaller for the model with the 5 predictors and for the model with the 2 predictors. Yeah? Simply because there's a stronger bias. All right, so and our R squared for multiple regression is at least as large as the R squared values for the separate bivariate models, right? So that means the multiple R squared has to be at least as large as the the largest square of the bivariate correlation between one of the predictors, and so a given predictor and the outcome variable, right? It cannot be smaller than the square of the largest correlation of a single predictor with the outcome variable. Makes sense, right? So the prediction, because if all other variables would not predict anything and would have a correlation of 0, then the model as a whole would still be as good as this single predictor that has a correlation with the outcome. So that means the multiple R squared cannot be smaller than a single, so the largest single R squared. Okay, so let's now take a step further. So we stated above that so in case of a model with two predictors, so that our first regression coefficient, so for our first predictor variable, measures the net effect of x1 controlling for the other predictor, right? So holding the other predictor constant. And what is also often said is that it means we partial out the second predictor. Yeah, in the same way, so our regression coefficient for the second predictor, so measures the net effect of x2 controlling or partialing out the effect of x1. So that's the reason why regression coefficients and multiple correlation are also called partial regression coefficients. Yeah, so they're called partial regression coefficients. So that raises the question, what does this partialing out mean? You know? And in order to understand what partialing out means, so we need to understand partial and semi-partial correlation. Is another question that is maybe a little bit hard to understand when you think about it for the first time, but it's important to really understand multiple regression. Okay. So partial correlation. So that partial correlation means, so we measure the relationship between two variables while controlling for, right? And it's also holding constant the effect that the third variable has on both of them. And we also have semi-partial correlation, and just the relationship between two variables while we are controlling for the effect that a third variable has on only one of the two on the others. So that is partial and semi-partial. We'll have more examples in a second, so that makes it clear. And both the semi-partial and the partial correlation can be generalized to situations where we have more than one variable that we want to control for. Yeah, so we call that first order semi-partial or partial correlations when we're controlling only for one third variable. And we call it second order semi-partial correlation when we control for two variables and so on, right? Third order, fourth order, whatever, how many other variables you want to control for. And so accordingly, our normal bivariate relationship or normal bivariate correlation between two variables is called a zero order correlation, right? So of course, we're not controlling of any third variables. So that's just a reminder, right? So what is a zero order correlation or bivariate correlation? So we have two variables, right? So that here represented by these two circles, right? It's a Venn diagram. So that is X, that is Y. And then we have this overlap between our, right, if in case they're correlated between our two variables. And then the squared bivariate correlation coefficient represents the portion of variance that is explained in each of the two variables, right, by the other one. And so that means that is, so roughly, right, it's not mathematically exact here, that relationship, but it's roughly, so the proportion of A, so on A plus C times A plus B. So what is the, right, so what is the proportion that B explains in C and that C explains in B. Right, so you could also see it like that way. So what is basically the portion of A for this entire, for A and B, and what is the portion of A for A and C. And then again, so that the idea is that, so this area here is 1. So to see, right, so that just to keep it in mind, so it is how much of the total variance of Y is explained by X, right? So that corresponds to this area A here in A plus C, so it's the entire circle, and so the other way around. So of course it's symmetrical. So how much of the variance in X is explained by Y? Okay. And what does partial correlation mean, right? So it means we control for one or more other variables. So let's assume we want to control for so the correlation between So we want to know what is a partial correlation between X and Y, and we want to control for Z. So what are we doing? So we are just removing the influence of Z from both X and from Y. So that means what remains from X when we remove the influence of Z. So then it just what remains is A plus Z, right? So it's basically, yeah, so I hope you can see that. So here I'm tracing that. So what remains from the total variance of X, if we remove so the part that is explained by Z, then it's just A plus C. Yeah, so this entire portion here is removed. And if we control for the influence of Z on Y, then we do the same thing, right? So we cut out so the overlap between Z and Y, so what's explained in Y based on Z, and then what's left is C and F, right? So these areas that here are called C and F. And then the partial correlation is simply, is basically what is this overlap here between these residualized parts of X and Y. So how much of the variance of Y that is not already explained by Z can be explained by X, right? And the other way around, how much of the variability in X that is not already explained by Z can be explained by Y. Yeah, so we are basically, so you can see a partial correlation, and that's exactly what it is, as a correlation between regression residuals. Yeah, so we are predicting X from Z, and then we are taking the residuals. So we're taking what is basically not explained in X from Z. And we have a second regression model where we're predicting Y from Z. So these are our predictor, Y is our outcome. And then we take the residuals from this regression. So that is a variance in Y that is not explained by Z. And then we are correlating these two residuals, right? So the X residuals and the Y residuals each other. That is partial correlation. That is basically the unique variance that two variables share. Unique, so that means unique that's above and beyond what they share with Z. Okay. And now let's think about what the semi-partial correlation means. So that means, again, if I have, so I want to know, so what is the correlation between Y and X? But this time I remove the influence of Z only from one of the two. So let's say from X. So that means, again, right, I could predict X based on Z. Then I have the residuals of X, right? So the part of X, so the portion of or proportion of variance in X that is not explained by Z. And then I correlate this residual with Y, but Y I leave unchanged. Yeah? That would mean I residualize only X on Z. And I could do the same thing with Y, right? I could residualize Y and could leave X unchanged. Yeah, then I could say basically so for how much of the variance in X, so total variance in X, can be explained by Y that is not already explained by Z. Yeah. Okay. So I remove the influence of the third variable only from one of the two. Right, I don't want to talk too much about the formulas here. That is basically more FI. It's more important to me that you understand the underlying principle. So why would you want to compute a partial correlation? Obviously, it's important for regression, but so you can use it as a measure on its own. That is useful in many situations. Well, let's say we have three variables that are all significantly correlated with each other. Yeah, so we're using bivariate correlation. So they all have significant relationships with each other. But we want to know whether the relationship between two of the variables is due to or partially to both sharing important variance with the third variable. Yeah. So let's assume, so we have methamphetamine users. So the drug use is significantly correlated with antisocial behavior. However, so we might have a third variable that might be relevant here, and that is poverty. right? So, and what we want to know is, so poverty is probably related to both, right? It's correlated with both. It's correlated with antisocial behaviors, and it's correlated with drug use. So, and we want to know, is the correlation between drug use and antisocial behaviors, is that actually, can that be explained fully by their shared variance with poverty? Or is there something unique about this relationship between drug use and antisocial behaviors? So do drug use and antisocial behavior, so are they associated beyond their shared variance with poverty? Right? That's a question that we could answer with partial correlation, right? So we run the partial correlation between drug use and antisocial behavior while we're controlling for poverty. But it means, so what we are doing is we predict drug use from poverty. We predict antisocial behaviors from poverty. And then we are taking residuals. So then we have basically the portion of variability in drug use and the portion of variability in antisocial behaviors that is not related to poverty. And then we see if these two unique portions of variance are still significantly correlated with each other. So is there a unique relationship between the two that is unrelated to poverty levels? That's a question that we're asking, right? So, and here you see these Venn diagrams, right? So is there something, so we have, right? So let's see antisocial behavior here, we have drug use, and then our X2 variable is poverty. And this KF was actually, I did that on purpose. So that, so there is actually no, so that basically all the variants that drug use, right? So this green circle, right, is antisocial behaviors. The blue circle is drug use. This here is the overlap here in the middle. And actually, so this entire overlap is covered by poverty here, and this fictitious, so just I constructed that, right, to make a case how that would look like. So that means that there is no unique relationship between antisocial behavior and drug use that is not also shared by poverty. That does not mean, so be cautious, it does not imply a causal influence here, right? That is just correlational. It's about unique, that doesn't mean that poverty is a causal factor here. That's a completely different question. It's just about whether there's a unique relationship between antisocial behavior and drug use. So let's assume for this fictional data, so that's the zero orders of the bivariate correlation, so not including poverty between drug use and antisocial, would be 0.33, right? And so, but if we are removing all shared variance with poverty, yeah, so do the two variables, do drug use and antisocial behavior uniquely share any leftover residual variance? And so that would, the answer might be no, they actually do not, as is illustrated here, right? In this case, so do not share any, so no significant variance with each other. All right. So how does partial correlation relate to regression? So under the assumption that, right, so that for conducting multiple regression, so like making inferences on multiple regression, so the partial correlation between the outcome variable and predictor 1, so x1, controlling for x2, right, on both of them, on the outcome and the xy, that estimates a correlation between y and x1 at every fixed level of x2. Yeah, so that is the interpretation of the partial correlation in the framework of a regression. And if we would control x2 by considering a subpopulation of all subjects that all have the same value on x2, yeah, so then the partial correlation between y and x1 estimates a correlation between y and x1 for that subpopulation. Okay, so why would we want to compute a semi-partial correlation? So, and again, before we talk about regression, so let's talk about some other scenario where we might be interested in doing that. So the semi-partial correlation is most often used when we want to show that some variable x1, yeah, adds incremental variance in y, yeah, above and beyond some other variable x2. And that is exactly what multiple regression is about. So that is what multiple regression is about, right? If you want to know, does any predictor add variance above and beyond some other predictor? And so the regression rates are actually closely related to semi-partial correlation coefficients. So they're not 100% identical, but they're closely related. All right, so but let's first talk about so some general example. Let's assume, so what we wanted to, what we're focusing on is pilot performance. And we want to know whether, so there is some unique relationship between motor skills and pilot performance that is not already explained by the relationship between between cognitive abilities and pilot performance. Yeah. So wait a second. So what we would do here is so we would basically. So we would residualize x1, yeah, on x2. So that means we would remove so all the variability so in x2 that it shares with, so all the variability in x1 that x1 shares with x2, right? So all the stuff that is not specific to x1, but variability that it shares with x2, we would remove that, right? So we would predict x1 from x2 in a regression model, and then we would use the x1 residuals and would see, do these residuals correlate with pilot performance, yes or no? And in this case, they would, right? So we would have this little snippet here of overlap. So that means in this case, x1 would contribute something that is unique and specific to pilot performance. That is not already cannot be explained by its shared variance as cognitive abilities. So motor skills would add something unique here. Right. So how exactly is semi-partial correlation related to regression? So regression is basically, not exactly, yeah, but basically about semi-partial correlations between the predictors and the outcome variable. So that means that each predictor is residualized on the other predictors, yeah, but we do not residualize y. So that means we basically in multiple regression, so we account for, right, that is what we was said, we are controlling for the influence of the other predictors. So we are basically, we're asking, and that's what the regression rate reflects, what is the unique contribution of this specific predictor that is cannot be accounted for by the other predictors to our outcome variable. Yeah, but we do not residualize y, not the outcome, only the predictors with each other. So then means for each predictor that we add to the model, we ask, so what is the unique contribution of this predictor above and beyond all other predictors? So what is the increment in R squared when adding this predictor to our model? And so if we have a model with two predictors, right? So then, so this is a formula for our standardized regression coefficient. So this is our beta. This is a formula for the semi-partial correlation, right? So where we have the correlation between y and so our outcome variable and the first predictor, and we are basically we are removing the so the shared variance of the second predictor from the first one. And you see that they're identical, these formulas, except for that this is the square root, right, from the denominator. So we're taking the square root of the denominator. All right, so that's the regression. That's why the regression coefficient can exceed 1 in absolute values. The correlation cannot. But the important takeaway here, and also from the formulas, is that so the value of the regression coefficients depends on three things. It depends on the correlation between the predictor and the outcome. It depends on the correlation between the other predictor and the outcome, yeah, or all other predictors, right, in case it's more than two. and it depends on the correlation between the two predictors. Yeah? If the two predictors do not correlate, then it doesn't actually matter. It makes the regression much easier, and the interpretation of the beta weights more straightforward. All right, yeah. So that's the last thing that I will cover today. So basically, what we want to know, right, always in regression is what is the relative importance of a predictor, of an independent variable, of an explanatory variable in an equation. And we can measure that in two ways. We can measure that by the amount that r squared would drop if that variable were removed from the equation, or by the amount that r squared, so basically it's the same thing, that's the first way we can tell, or by the amount that r squared would increase if that variable were added to the equation last. That's very important. It has to be added last. It has to be added to everything that's already there, right? So what is the change in r squared that is contributed by this particular predictor? And this amount can be measured by the squared semi-partial correlation. So that means the squared semi-partial correlation between a predictor and the outcome variable, controlling for the variance that this predictor shares with all other predictors. That is the r squared change that this variable causes. That means if we would remove that variable from the regression equation, the r squared would be reduced by this amount. Yeah? So it's a measure of the unique contribution of this particular predictor to the outcome variable. Or we may measure it by the relative magnitude of the beta weight, yeah, by the standardized beta. But if we have more than two independent variables, so more than two predictors, the first method is preferable. First method is always preferable. So, right? So it just, I wanted to add that for sake of completeness, of course, a beta weight, as that is why we have the standardized beta weights, so to make them comparable, but we should always focus on the change in r squared, always. All right, so, and just to make that picture complete, right? So what is r squared? And so r squared, so we can express it in two different ways. So r squared is nothing but the squared bivariate correlation between the first predictor and the outcome, plus the squared semi-partial correlation between the second predictor and the outcome, right? And so the squared semi-partial correlation is controlling for the basically influence or the shared variance of the first and the second predictor. Or, now you can also, that is exactly the same, it is the squared bivariate correlation with the second predictor and the outcome variable plus the semi-partial correlation of the first predictor with the outcome variable, controlling for the second one. Right? So those two terms there are equivalent. And so the squared univariate correlation between outcome and predictor is simply the proportion of variance, of y variance, of outcome variance that is explained by the first predictor. And so the squared, correlation between outcome and second predictor is the proportion of the variance in y that is explained by the second predictor, right? So again, ignoring the first one. And so our semi-partial, so the squared semi-partial correlation between our outcome variable and the first predictor, that is a proportion of the y variance that explained by x1, so by the first predictor, beyond that variance that is already explained by the second one. As it's a unique contribution of x1 to the outcome. And so the squared semi-partial correlation between the outcome and the second predictor is a unique contribution of the second predictor. Yeah? So that is the amount of variance that explains the outcome that is not already explained by the first predictor. But that is really important to understand. Really, really important. Okay. So just to circle back to the partial correlation, right? So the partial correlation between and then of course the same is true for the other way around. So the partial correlation between our outcome variable and one of the two predictors, so let's say the first predictor, yeah, controlling for the second predictor, that represents a proportion of the variation in y that is explained by x1 relative to the variation that is unexplained by x2. Yeah, so that's basically that is a ratio. So it is the ratio of the semi-partial correlation coefficient between outcome and first predictor to the proportion of variance that is not that remains unexplained by the second predictor. Right? So that is the square of the partial correlation coefficient. So just to basically get it all together, the relationship between these partial and semi-partial correlation coefficients to the beta weights, and more importantly to R squared. Oh, okay. Yeah, so in here, I just wanted to show you, because I mentioned, then I will really stop for today, because I haven't mentioned it explicitly here, right? So this shaded area here, so that is always a shaded area. So for the first Venn diagram, that is the proportion of variance in y that is explained by the first predictor. Yeah. So, and this dashed, or I don't know what to call it here. So this area here, that is the proportion of variance, so of y variance, that is explained by the second predictor, right? That is not already explained by the first one. Yeah? So that is the one that is not, so that is basically beyond that explained by the first predictor, right? So that corresponds to the square of the semi-partial correlation coefficient. Yeah? So that is basically beyond the unique contribution, so what uniquely explained in y, right? So in addition to that, right? And that is basically just, so that relates to these equations here, right? So these diagrams here. All right, so just very quickly, so this multicollinearity, I just want to check whether there's anything you need that I haven't mentioned that's so different than for simple regression. Wait a second, that you need. All right, now I think we are good here. And then if power analysis, so the rest is relatively easy, because it's more or less exactly the same as for the bivariate regression, so the simple linear regression. But so next week, so in our, of course, we will talk about multiple regression so in the lab section, and we'll do like a multiple regression example, and maybe we can also do a robust multiple regression, so that you have all seen that. And and then next week in class, I will probably talk a little bit more about multiple regression. So most importantly, so I want to show you how to test interactions in the regression model, which we haven't covered yet, and that's new and very important. So that's one thing that I would like to include, and then we will talk about regression with dichotomous or categorical predictors, which is basically analysis of variance. So that's what we are going to start to talk about next week as well. So just an outlook. Alrighty, so any questions? No? Yeah, if you have, I mean, so it's very important. If you have, if there are things that are unclear or confusing, so please go over the slides, so check and let me know if there's things that you feel we should discuss again, or that remained unclear. So that, because it's important, and it's important to understand, and it's probably, it probably requires a little bit thinking about it. So because all these the semi-partial correlations that requires a little bit thinking and for yourself, because the terms are also a bit confusing. So they all sound very similar. If you know what I mean. So, but it's important, right? So if you feel after studying the slides, so and based on what the textbook describes, if you feel it's still unclear, then let me know. Yep. All right. Okay, then good luck with. Oh, yeah, one more thing that I wanted to mention. So you will get the graded assignments very soon. Yeah, so that will be tomorrow. It's tomorrow, Thursday. It's the very latest. So, and then, yeah, if you have any last minute questions for assignment, for the assignment that's due today, so I will check my emails. Okay, then I'll see you next week, and hopefully you give me some good feedback. All right, bye.